Welcome back, everybody, and welcome to the session on constructing a neural network from scratch. And this is part 3 of the neural network machinery and lectures. And after that, we are going to implement these to solving differential equations for neural networks. So today, we are going to look at how we can build our own network. In the lecture notes, you will find examples on a more general code, which you should feel free to use as you would like in project number 2. But today we're also going to look at some simpler steps which we can take and how we can include the various elements. This code is applied to, in this particular case, to the so-called MNIST data, which is a data collecting a series of handwritten numbers, and it's a classification type of problem. The exercises and lab sessions in this week deal with you essentially constructing a backpropagation part for the neural network code in project number 2. And we will continue with our discussions of project 2. And also the exercises this week can be seen as an extension from the previous week where we did the feed-forward pass. Again, I would like to remind you of some of these textbooks on the mathematics of deep learning, which is a rapidly evolving field in mathematics. There's also a reminder on the on books with hands-on material. So if you go to Sebastian Raschka et al.'s textbook on machine learning with scikit and PyTorch in chapter 11, you will see the basic steps for essentially solving project number 2 with both the feed-forward and the backpropagation part. And in chapters 12 and 13, if you want to use PyTorch, then there are quite detailed examples on how you can write a neural network code in PyTorch. Today, after we have written our own codes, we are going to look at how we can implement this with TensorFlow, which is another very popular library. So TensorFlow was released by Google in 2015, and it's their deep learning library with lots of additions. And PyTorch was released by Facebook in more or less the same time, and it's obviously Facebook's alternative. Now, with TensorFlow, we will run these using Google Colab, because sometimes some of you may experience problems with installations and dependencies of TensorFlow, depending on which type of operating system you have. And sometimes it can be a hassle to actually set up the dependencies correctly. So when we move into TensorFlow, I will also show you how you can use Google Colab and run the TensorFlow examples, which you will find in the lecture notes here. So again, using automatic differentiation is a very important topic. And we remind you of how to use that in different examples here. Now, what we did last week was to discuss the architecture of the network. And in the exercises last week, we looked at how we could set up your inputs and scalars, and outputs. And these could be scalars. In the lectures last week and the week before, we looked at a simple case where we just had scalar in and scalar out, and we had just one hidden layer or no hidden layers. And we extended this to have one hidden layer with 2 nodes. We could have 2 input nodes. And gradually, this translates into a slightly more advanced problem with us setting up the input eventually as a matrix or a higher order array, which we normally call tensors. And the output could also be a matrix. It could be a vector, or it could just be a scalar. And this becomes very important when we are setting up the input parameters to the network, with the way we set up the weights and the biases and the parameters we need to train. I also want to remind you that backpropagation, which we have been discussing again and again, is, when we look at automatic differentiation, is nothing but automatic differentiation in its reverse mode, which mathematically means us applying the chain rule again and again in order to find the derivatives or the gradients of the different parameters at each layer. Then when we have these expressions, so the backpropagation algorithm gives us these expressions, then we can implement the gradient descent and update the parameters. So the gradient descent itself is not the same as backpropagation. And when we do this, we need to define the activation functions for the hidden layers and output layers. We need to define optimizers, and this is in particular important now when we are dealing with the exercises this week, is to set up the optimizers, which we had in the exercises for 2 weeks ago, when we looked at different ways by which we could implement gradient descent. Then we need to define cost functions and possible regularization terms. We need to initialize weights and biases, and we need to fix the number of iterations for the feed-forward and the backpropagation part. So when we derived the backpropagation equations, or the backpropagation algorithm in simpler terms, what we need to is to set the input data and the activation functions of the input layers. And this is essentially what we will do in the example. So the example which follows now is a simple example with less flexibility, because we're going to set up a neural network with just one hidden layer. And that's why we have this label C1 and A1 for the output. So C1 is the input to the activation function, and A1 is the output of the activation function. And this is fed into the output layer. When we perform this feed-forward pass, we will, in general, and the code which follows afterwards is actually a code which allows you to define neural networks with more than just one hidden layer, so it's a little bit more general. And then we could define layers which go from 1, 2, 3, up to uppercase L, which now stands for symbol for the output layer. And the first hidden layer has obviously labeled 1, and the final one has labeled L equal the uppercase letter L. Then what we did last week when we derived the general algorithm was to find this quantity which we call the output error, which is a kind of misnomer, but that is defined in terms of the derivative of the activation function and the derivative of the cost function with respect to the output from the output layer, which is this AJL, and J stands for a specific node. Remember now that when you write this as a vector, in terms of vector or a matrix, you have to keep in mind that this is given by element multiplications, which again in turn means that when you're implementing this in Python, it's simply written by the simple mathematics multiplication symbol. Then we compute the backpropagation error for the previous layers till we reach the final first layer, which is actually not labeled by number 1. So this is the layer right after the input layer. And then we have an equation here, which we derived last week in terms of the weights from the previous layers, this error, output error from the layer L plus 1. And then we have, again, the derivative of the activation function. So having derivatives activation function means that we can, if we use autograd, automatic differentiation, it can be useful to actually have this function here calculated using automatic differentiation. Alternatively, if we're not testing too many activation functions, we can hard code the derivatives. And as we mentioned, when you're setting up your project, you will not be penalized if you don't use automatic differentiation. It makes life easier, and it allows you gives you much more flexibility in the sense that you can test many more types of activation functions. And when you run a neural network calculation, you would typically test different types of activation functions. When you've gotten the equations here, then you have the gradients, and the gradients are then given by this parameter delta multiplied with the outputs from the previous layer. And this would be the update of the weights. And then for the updates of the biases, then we simply have the previous values minus the learning rate times the function delta J of L. And then when we are updating the gradients, we would simply use this function here. And then we would simply proceed by updating the different variables as we move on. And that is the backpropagation stage. And then we have new values. And with new values, we would then continue with a feed-forward pass and the backpropagation pass till our cost function doesn't change by some fixed amount, which we have determined. So if you're dealing with a mean squared error, this could be that we have fixed the change in the mean squared error to be less than, let's say, 10 to the minus 5. Now, the activation functions also have some specific requirements. They should be non-constant, bounded, monotonically increasing, and continuous. And they should also have continuous derivatives or derivatives which are simple to evaluate. And some of the most popular ones are the sigmoid function, as we discussed last time. We have the hyperbolic tangent, which is also widely used. We have the family of Rayleigh functions and the Euler function. So these are all types of activation functions which we are going to play around with. And you will typically see that often the Euler function tends to give better results. And then we have the leaky Rayleigh, and then we have the Rayleigh function itself, or the rectified linear unit. We are going to skip some of these things because these are things we are going to, which classification functions we are going to, activation functions is something which we will typically discuss when we run actual calculation. And it's pretty common to test different types of activation functions. For the output layer, the activation functions is normally different from the hidden layers. And for a classification problem, you will encounter either something like the sigmoid function, which spits out 0 and 1, or the softmax function, which we will discuss below here. And for regression tasks, what is common then is just you don't use any activation function at all. You just send out the value which you have as input to the output layer. It's pretty common to often run the calculations with the same number of hidden nodes and the same activation function for all the hidden layers. But you can change these, obviously. So if you go back, our model is then determined by these different points here from 1 to 7. And some of these bullet points here, they end up making up different functionalities which we have to test when we are implementing a neural network calculation. Because sometimes we may observe that with Adam, as a way to update the learning rate gives a better result than, let's say, root mean square propagation. Sometimes the activation functions like the tan H gives better results than the Rayleigh function. And this is something which we don't know a priori. So the universal approximation theorem, just to remind you of that simply states that with the one hidden layer, you can approximate a given continuous function to a specific error. It doesn't state what the error is. This is something which we have to try and play around with. And it doesn't say anything about which activation function gives the best result and how many hidden nodes you need, nor how many hidden layers you may need. So that becomes part of the modeling and thereby also the architecture of a network. And these are parameters which we would have to play around with. In the same way as we in project number 1 discussed a polynomial fit where we played around with different polynomial degrees of freedom, except that now the space of variables and functions we have to try and options we have to try is getting much larger. Okay, so in the examples which follow here, we are going to look at how we can set up a multi-layer perceptron model for classification. You can replace easily classification with a regression, as you will see in a more general program below here. So one of the typical functions if we have a binary classification problem is actually the sigmoid function, which we have encountered many, many times. The cost function, which we normally use in a type of classification problem, if you're dealing with a binary problem or a multi-classification problem, multi-class problem, is the so-called cross entropy, where we now take the log of this probability which we have defined, and we have 1 minus the output here times the log of 1 minus p of the probability which we have defined. And this defines what's internal inside here, the loss function, and we normally take the negative log of the probability distribution which we have defined. And this last equality means that we can interpret our cost function as a sum over the loss function for each point in the data set. It's pretty common in a multi-class classification problem to convert the data which we have into a string of binaries. And so that means that a number like 5, which is the one we are going to try to reproduce, so we are going to have 100 numbers from 0 to 9, we can then encode that one into just a binary. So you can see here, if you have 10 numbers from 0 to 9, you would then use an integer representation where you have bits 0 and 1. So when you have y equal to 5, it would be the 6th bit then, which is given by 1 here. And similarly, when you have 1, so the first bit would be 0. There's no 0 here, but there's a 1. So we just have a word which is given by bits 0, 0, 0 up to 1, and then zeros again. And this is normally called a one-hot vector. Now, when you have a multi-class type of problem, then your activation function at the output layer is the softmax function, which is in a way can be seen as a generalization of the logistic function, or the sigmoid that we've also been calling it. And the probability distribution for C-class classifiers is then given by the probabilities over the data sets and then multiplied with the different classes which we have. And this P is now given by the equation which you see here. And again, we will take the negative log likelihood and take the derivatives of those, and then we have the derivatives of the cost function. And all these equations are implemented in the program which follows below here. So if we do a plain binary classification problem, if you now want to make a slightly more general code, as you will see below in the lecture notes, then the problem which we would have to look at then is simply to take the derivative of this cost function, where the p's here are simply given by the sigmoid. And in this specific case, this is the function which we then would optimize and find the derivatives of. And we found that the output of from a specific layer is then given by this AIL, so I for node I. And this is again given by the exponential, where we now have the input C of I and divided by 1 plus the exponential of C of IL. And these C of I's are, as before, they are now given by these weights, unknown weights, which we need to define. And then we have the input, or sorry, the output from the previous layer plus the biases. So these are the parameters which we derived, or the variables which we derived in the previous lectures in part 1 and part 2. And in our case then, when we look at the final layer, then our cost function is simply given by now using T for the target value. So this is the values we want to target and output. And this contains now the log of A of I, which we are producing from the network. And similar, we have 1 minus A of I, which is the output from the sigmoid function, which you see here in the final layer, the output layer. And then this is just to repeat quickly what we have been discussing earlier. And when we take the derivative of the cost function with respect to these A of I's, this is the function which we get. And in case we use another activation function than the logistic one, we need to evaluate other derivatives. So just keep in mind now that here we are using the logistic function. If you prefer to use another activation function for the output layer, then you simply have to replace these derivatives with that expression, which corresponds to that specific function. If you use the softmax function, there is just some additional algebra you need to go through, but the calculations are not that more difficult. And here we label f as the activation function given by the softmax function. And in this specific case, the only thing which changes from the derivative of the sigmoid function is that we have a Kronecker delta ij here, depending on what's the variable ji here for the input to this one, and with respect to which z we take the derivative of. So these are just some simple manipulations of these equations, either the softmax or the logistic function, which then leads to slightly different changes in the expression for the derivatives. However, if we now have generalized these, so we can freely change different activations functions. And if we use automatic differentiation, we can then easily just play around with different activation functions. Alternatively, if we now want to set up a long list of activation functions, we need to hard code the derivatives. But this is something which is pretty standard to set up. And you will see in the example which we have below of a more general code that we have a long list of activation functions which define a class of activation functions with their mathematical expressions, which are hard-coded as a Python code, and their derivatives, which are also hard-coded. So I invite you to take a look at the codes when you're developing your own. So when we're now developing a code for the neural network here, and if we now link this with what we did in the exercises in last week, and the exercises we're going to do this week, we need now to collect and pre-process the data. We define the model and the architecture. As stated before, choose cost function optimizer. We're going to train the model. We are going to evaluate the model performance. We can also adjust hyperparameters. Now, one thing which becomes important now is the way we pre-process data and the way we collect data. So this MNIST data which we have, of course, is a data which consists of 70,000 images, and the size is 28 times 28 pixels, each label from 0 to 9. Now, for pedagogical reasons, and in order to be able to run these codes in a decent amount of time, which means some few minutes during a lecture, we are going to use a scaled down version, which consists of close to 1,800 images, which have a much smaller size. So they have 8 times 8 pixels. And these are the numbers from 0 to 9. That means that when we now are setting up our neural network, the number of inputs in a design matrix are going to be given by this number 1797. So think back to what you did in the exercises last week when you prepared your inputs in the feed-forward pass. We went from a scalar input to a vector input to a matrix. And in this particular case, the matrix is now given by 1797 times the number of features, which in this case consists of 8 times 8 pixels. So the number of features is actually 64. And you can easily see, as an example, if you have you want to build a neural network code which predicts the body mass index from measurements of height in meters and weight in kilograms. And if you have 5 persons, then along the first column here, you would have the height in meters. And then in the second one, you have the weight in kilograms. And then your output, which you want to train this model on with 5 data points, given by a 5 times 2 design matrix, this produces an output which is now given by the body mass index, the BMI. So since each input image here in the classification case we are dealing with is a 2-dimensional matrix, we would need to flatten this image into a 1-dimensional array to turn the data into a design feature matrix. So this means that we lose some spatial information in the image, such as locality and translational invariance. More complicated architectures, such as convolutional neural networks, which we will discuss later, they can take advantage of such information and are most commonly applied when analyzing images. So the first thing we're going to do here now is simply to load the data set. And these are the loaded digits, which is included with scikit-learn. And as we have done before, we're going now to set up the inputs in terms of a matrix. And we are going to make a first plot here just to see what it looks like. And in this particular case, you see some selected numbers, which we are plotting here. So this is number 8, 7, 7, 3, and 3. And for some of these numbers, they can actually be hard to distinguish. So this is a pretty scaled down image from 28 times 28 pixels down to 8 times 8 pixels. You see also that the inputs, they have a 1797 images, and then we have 8 of pixel width and pixel height 8. And this is now scaled to an image or design matrix, which has 1797 times 64 as dimensionality. So that contains all the images which we want to train. Similarly, if you were looking at the cancer data, which we have in project 2, you have something like 500 patients and 30 features. So then your design matrix goes like 500 times 30. Now, in this particular case, the human accuracy in recognizing these numbers is roughly 97, 98%. For some of these numbers, you really have to use a kind of goodwill to actually be able to recognize. I actually have problems with this number 8. Then we are going to do this standard train test splitting as we've done before. Nothing new here. We simply do a train test split. If you want to write your own code, there is an equivalent here, but we normally recommend using the functionality which scikit-learns offer. So if we now run this, we are now splitting our data into training and tests. So we have roughly 1,400 training sets and 360 test images, which were not included in the training. So we need to define the architecture and the model. So we set up a simple feed-forward. The simplest activation is this heavy side, but we are going, in this example, we are going to use the sigmoid function. The layers, we need to define the input. So the input has, each image has 64 pixels or features. So we would have an input layer of 64 nodes or neurons. There's a hidden layer, and in this example, we are going to use 50 neurons. That means that since each neuron in the hidden layer is connected to the 64 inputs, that means that we have 64 times 50, which is equal to 3,200 weights to the hidden layer. So these are parameters which we need to define and train in order to find the optimal values for these parameters. In addition, since we have 50 neurons, we are going to have 50 biases. So we are going to have, for the hidden layers, 3,250 parameters which need to be trained. So since we are building a multi-class classifier, not a binary classifier, we are going to need 10 nodes for the output because we have 10 handwritten numbers which we want to classify. So that means that this hidden layer is going to connect with 10 neurons or nodes in the output layer. So that means that if we now have 50 nodes times 10 neurons here, we will then have a connection which leads to a design matrix, a weight from the first hidden layer, which is the only one in this case, to the output layer, which gives us a total of 500 weights, as you can see here. So we had 3,250 parameters from the hidden layer, and then we have 10 nodes in the output layer, so 10 biases, plus 500 weights. So we're going to have 3,250 plus 510, which gives us 3,710 parameters to train here. That's a total number of parameters which we need to train in order to figure out whether our model is doing a good job or not. And when we are setting this up now, we need then, and you will recognize these codes from some of the examples from last week and the week before. So we specify the number of hidden neurons, the number of categories, which in our case is the number of output nodes. I specify the hidden weights, so I'm initializing the weights and the biases for the hidden layers and the output layer. And in this case, I'm just setting the hidden bias in both, and the biases in both the hidden layer and the output layers to 0.01, just a small number. So let's run this cell as well. And then we have set up those parameters. And now we are going to, after we do the matrix multiplications, because the input to the hidden layer is going to be given by this Z. And we have the design matrix times the weights plus the biases. And this is fed into the function f, which in our case is going to be the standard sigmoid function. And that produces an output. And that output is fed in to the output layer, which we label with an uppercase letter L. And in our case, the output, which is this A of L, is going to simply be given by the softmax function. And here we have the feed forward pass. So we are performing the matrix multiplications for the hidden layers. And we are finding the input to the activation function for the hidden layer. Here we set up the output input, also the input to the output activation function, which is the softmax function. So this is now given by the softmax function, which you see here. So it returns these probabilities here. So this is just a feed-forward pass. And if we look at that one, what we get now is not a very good classification. So we make a predictions on these images which we put in. And the prediction for the image, which is now labeled as a number 8, is actually wrong, because we were actually trying to reproduce number 6. This is just an example. And as you will see when we move down here, now we are actually trying to set up the backpropagation part. So this comes down here, and we're also adding some regularization term, and this is pretty common. So as we said, we have 3,250 weights and 510 weights and biases in the output layer, 3,250 in the hidden, and these are the total number of parameters. So we need to perform these different matrix vector multiplications and matrix multiplications. We translate our numbers into binaries, and we have a feed-forward pass here. And then we have the backpropagation pass, which we are going also to practice this week. And pay attention now, since in the previous week, we did the exercise where we set up the dimensions correctly. It's actually difficult it's very unlikely that you will have problems with setting up the backpropagation part if you have set up the dimensionality correctly in the feed-forward pass. So here you can see an example on where we set up the weights and the biases. We have the derivatives of the activation function, which is given by this one. And then similarly, we find then the gradients of the output weights. We have the gradients of the hidden weights and the hidden bias. And these are then returned to this function, and we are setting up a learning rate. We have a parameter lambda for the regularization term, which then is set just to 10 to the minus 2 here in both cases. And then we set up in a very brute force way the different gradients. So if we run through now, you will see that the accuracy on the training data when we have just done one iteration is 0.14. And this is done on the training data, as you can see here. And the way we calculate the accuracy is simply by, so this is the accuracy in the old training data, and then we have a new accuracy when we've done a backpropagation pass, and this is 0.09. Ideally, we would like to have 1, so that we have 100% fit. And you see that in this case, with these two parameters which we have here, this is not a very good choice for the parameters. And this is not a very impressive number either. So it means that if we want to present some results where our training is at the level of less than 10%, this is not something we would brag about. So we would typically then do a grid search. We could test learning rates. And in this particular case, we just have a very primitive update of the learning rates. And this is where you would have to plug in the different methods for updating the learning rate. As you can see here in these expressions, we are just implementing the simplest possible gradient descent. So this program is deliberately kept as simple as possible and as transparent as possible, so that you can see where you can upgrade things. Now we are going to make an array of different values. So we start with eta 10 to the minus 6, which is actually a value which you will often find is not good enough. Actually, you can narrow this down to learning rate values between 10 to the minus 3 to 10 to the minus 1. These are much better values than starting with 10 to the minus 6 and 10 to the minus 5 and even 10 to the minus 4, because in most of these cases, you're actually going to have a network where the gradients barely change the values of the parameters. And then we have regularization parameters, which typically span from 10 to the minus 6, 10 to the first, or even just 10 or just 1, and so on and so on. So this is a new set of parameters which we will need to set up. And then we would need to, if we do a stochastic gradient, we would have a set of epochs and mini batches which we need to set up per iteration. And here we have a more object-oriented code, which is a class for neural network. where we now have defined different parameters, the hidden neurons. So everything is prefixed here. There is less flexibility. And the code which you are writing now in the lectures is slightly more flexible in the sense that you will define the number of hidden layers, the number of hidden nodes, and you will also define the type of optimization function. But you see now that the categories and the epochs, the batch sizes, the learning rate, and also the lambda parameters, so these are just set here, but then they are changed by you. You create the biases and weights. There's a feed-forward pass. There's a feed-forward for the output layer, where you then have a different activation function. And then there's a backpropagation part, which now sets up the gradients, as you can see here. And then when you have the gradients, then you set up the equations for the updates. And these are the updates of the weights and the biases in the output layer, and similarly for the hidden layers. And this is something which one can generalize to more layers. But here we're just keeping this very, very simple approach here. And then we have the predictions, we return probabilities, and then we have the training part, where we are now simply running over all the different rates which we have. So if we want to evaluate this model, we are now going to use the accuracy as one parameter. And for the quality of the model which we have set up. And this simply counts the number of correct classifications and divides by the total number of data points which we have. And an accuracy 1 means 100% classification. If we now run this code here, if we now just start it, we can, as you can see here, this is run one time. You see now with one parameter for lambda, one parameter for eta. In this specific test, we get a accuracy score on a test set, which is pretty good. And here I have hard-coded the accuracy score in this line here. So that simply counts the number of correct classifications compared with the cases which we have. So we can then adjust the hyperparameters, and we can run here. And if we run this code, you will now see that it gives you different types of outputs, and it simply collects the values as we did in project 1. But in project 1, we had simply the parameter lambda, but now we're actually running this with the learning rate as well. And what we would typically do then, when we are done, is to make a plot using a software like Seaborn, and then we would make a heat map with the values themselves and find those which are the best ones. And as you can see here, when we run through it, the classification is getting slightly better. And when we are now moving into a learning rate of 10 to the minus 3, we see also that the classification, so here we're getting close to 96% on the training. We have a 93%, 94%. This is a 96%. And now it's dropping down to a smaller value. And this is just going to keep running here for us, as you can see. And we will get a accuracy which is going to be roughly around 96%. And in some of the cases, we're also going to encounter some overflow. And some cases, when you're running this with scikit-learn, will also give you results which are not entirely converged as a number of iterations. So till now, what it seems is that on the test set, we are, with this model which we have chosen, we are running into an accuracy which is 96%. And this is the best which we are going to get with these calculations here, which is not impressive if you think that a human, on average, on that scaled down set of 100 numbers, has a score of 98%. So you will see now that when we increase the number of layers, etc., we are going to get better results. You should also keep in mind here that what we have done is to run the calculations with no optimization of the learning rate. So we are just running a plain gradient descent. And when we visualize these results, so this is still running actually, and you will see now that when we increase the learning rate to 1, the results are getting worse and worse, as you can see here. So this accuracy is really getting bad. Now we can visualize this, but I wanted to show you how you can implement the same case with the scikit-learn. And scikit-learn uses Adam as a default. In this case, we are using the activation function for the hidden layer as a logistic function. And we are dealing with the classification of the MNIST data with the softmax function. And we are using the same values for the learning rate and the same values for the hyperparameter lambda. So if we run this case with scikit-learn, which has a deep learning neural network functionality, but it is not at the same level as you would find in TensorFlow and in PyTorch. However, in this particular case, even with just one hidden layer, and you can see now that with the stochastic optimizer, we are still having some problems with the number of iterations, but you will actually get an accuracy on the test set, which is going to be better than the one we had with our simple gradient descent code. So if we scroll down here, we'll see now that with this learning rate and this lambda value, we are going to get a 98% accuracy, which is close to what humans get. And you can see several cases here where we're getting a 98% accuracy, which is actually pretty good. And here we are even getting 99% accuracy, which means that the neural network here, even this simple neural network, is actually doing a pretty good job in classifying the handwritten numbers. And it's here, for this specific case, it's actually doing better than an average human. And you will see many cases here for many learning rates and lambda parameters where you're getting a pretty good test score. And in our case here, it's actually this set, which you would then use as the best set. So when you make a plot with Seaborn, for instance, and you can look at these visualizations in the Jupyter Notebook, you will then find that the best parameter is one which has a learning rate of 10 to the minus 3 and a lambda parameter of 10 to the minus 2. And that gives us a score of roughly 99%, which, as I said, is better than what a human will do. And you see also that you have several values here, which actually these cases here with a learning rate which is larger, normally between 10 to the minus 3 and 10 to the minus 1 are the results which we find, which often give the best predictions. You can see here that we're pretty close to 99% for quite many learning rates and lambda parameters. So the recommendation then is that you should use one of these optimizers and not do a plain gradient descent. Okay, so after we've done this, we are now going to look at how we can implement this with TensorFlow. And after that, we are going back to our own more general code. And we're going to take a look at how we can generalize these ideas which we put forward here in terms of a more general object-oriented code. And you should feel free to use these examples when you are solving project number 2 here. So let's try to recapitulate a little bit of what we did before a small break. So when we use the Seaborn package, we can then easily visualize the results as a function of the learning rate, which you see along this axis. And we have the best learning rate, which is roughly 10 to the minus 2, which stands for this variable 3 here. So 0 is 10 to the minus 6, and then we get to 10 to the minus 3, 10 to the minus 2. And on the training of the test, on the test, we see now that the learning rate roughly 10 to the minus 3 gives us an accuracy of 96%. This was a case when we didn't use any kind of fancy way to update the learning rate. Now, the example which we showed with scikit-learn was an example where we now use a default stochastic gradient descent with Adam as a method for updating the learning rate. And in this particular case, when we now look at the plot, and now I'm using Google's Colab just to change a little bit. And in case you have had problems with installing dependencies, etc. To run everything on Google Colab is something which can be pretty fruitful in case you're struggling with these kind of dependencies. And if you now look at the training accuracy when we deal with a neural network classification problem for these handwritten numbers, you see now that training gives us roughly 100% accuracy when we had learning rates of 10 to the minus 3 to 10 to the minus 2 here. So this is a pretty good classification case for the training. We will say it's perfect for the training. And you see also that for the test case, we are actually having a whole series of values when the learning rate was 10 to the minus 3, which is here, for along a big range of lambda values. So we're actually having a test precision, which is 99%, which is pretty good. And which was much better than the simple case which we put up. Now, when you're dealing with TensorFlow, this is a very flexible library which allows you to train and adapt and use many of the famous deep learning methods, actually basically all famous deep learning methods. So you will see also next week when we compare with our own codes with the convolutional neural networks from TensorFlow. You can do recurrent neural networks. You can essentially plug in all the advanced deep learning methods. And the way you would include it is simply to import TensorFlow here as TF. You can obviously install this on your laptops. If you have problems, as I said, if you have problems with dependencies and installing things correctly, I would normally recommend using Google Colab. So I'm showing it here because it's useful to have seen it, and many of you have already used it, and feel free to continue using it. So in this specific case, I'm taking the handwritten numbers again. So I'm just repeating what we did in the previous case. And you see the same examples. I have the same seed which I'm using. So I'm importing TensorFlow, the layers, the models, which is essentially a sequential model. I'm going to have a dense layers. I'm including the optimizers, the regularizers, and then I'm also doing a set of categories because I want to do a classification run. So I set up the train test split as before, so you can interface functions from scikit-learn with TensorFlow, and you recognize again train test split. We're actually using scikit-learn's library for importing the handwritten numbers. You could have used TensorFlow's function for doing so as well. Now, the reason why I do it here is simply because I want to show you how you can interface scikit-learn with TensorFlow. And we are setting up much of the same as before. We have the number of epochs, 100, batch size, 100, neurons, layers. We have layer 1 with 100. We have layer 2 with 50. We have categories, 10 categories. And we are setting up the space for eta values and lambda values. And now I'm setting up simply a model here, which contains, it's a sequential model, goes step by step. It adds one dense layer. This is the first hidden layer with the activation function, the sigmoid. And then I also have a regularization term of L2 type with the parameter lambda. I do the same with the second layer. I have as input here the number of neurons. The activation function is the sigmoid. And then I simply have the final dense layer, which is my output layer with the categories, the number of categories, which are 10. These are the 10 handwritten numbers. And then I have an activation function, which is a softmax. I specify my optimizer for the learning rate to be a standard stochastic gradient descent. So this just as a plain stochastic gradient descent. You can specify root mean square propagation, Adam, etc. And then my loss function or the cost function is the categorical cross entropy. And you see the optimizer is this one, and the metrics, which I want to spit out, is the accuracy. And this is the way I would simply create my neural network using TensorFlow. And you would find similar ways of doing that if you use PyTorch. And for PyTorch, in Rashka's textbook, there is also a link to the GitHub address. And in the GitHub address, essentially every chapter of the textbook is contained as a Jupyter notebook, obviously without derivations and equations and so on. But all the codes which are discussed in the textbook by Rashka et al. Are given in their GitHub address. And there you can look at PyTorch implementations as well. And I myself normally prefer to use PyTorch because I've had less problems with installing different dependencies. But this is something which we leave up to you, whether you want to use TensorFlow or you want to use PyTorch or simply use your own code. So in this course, at least for projects 1 and 2, using your own codes is actually what we are doing. But then in project 3, it may be that you would like to test other algorithms, that you would like to test convolution neural networks or recurrent neural networks. And in that case, it may be useful in project number 3 to use either PyTorch or TensorFlow as libraries. And you can see now, we run through here. This is just an output from TensorFlow. And then I've been using, finally, my Seaborn plotting optionality. And then if I look at my test accuracy, now I have 2 hidden layers. So with 2 hidden layers, and this is something which you are going to play around with when you are setting up your neural network code, is what you see now with the same stochastic gradient, almost the same stochastic gradient optimizer. When we have 2 layers, I'm getting an accuracy of 98% on my test accuracy. And in my previous case, I had 99% with only 1 hidden layer. So sometimes you may actually see that 1 hidden layer gives a better result than 2 hidden layers. But we don't know that before we have run the calculations. And coming back to the setup of the model and the architecture and so on, this is one of the things which we have to live with when we are dealing with applications of deep learning methods. So this is a typical example of where we thought that perhaps we make the network more complex, we have more hidden layers, we're actually not getting better results. So there are examples on the breast cancer data with KERAS. I just invite you to take a look at that one. This contains a slightly more detailed study of the different features. And then after that, you will find the more general code, which we have discussed. So if we move down a little bit, I'm not going to go through all these outputs here because there's a lot of runs which I've made. But we are going to look at our own more general code and how you can actually start setting up your own more general neural network code. So feel free also to use many of these examples. So building a neural network code is something which is fun. And if you have time and you want to use classes or you simply want to reuse what we have here, feel free to do that. So here we have a code, a more general code, which was actually developed by 2 former students of this class, Eric Reber and Gregor Kaida. And they did this during the spring of 2023. And they took the codes which we have seen till now and made a slightly more general one. So in this specific case, what we have is a class which now contains the different types of implementing the gradient descent schedules for the learning rate. So this is the first class which we encounter here. And that contains AdaGrad, it contains AdaGrad with momentum, it contains root mean square propagation, which has a kind of momentum, and it contains Adam. So these are actually the methods which you would use when you're setting up your own neural network code, a more general one. So this is just to show you examples on how you could write a more general object-oriented code. So in this specific case, we would have a momentum scheduler, which we can simply test here by plugging in a specific value for the learning rate. And then if we are using the Adam scheduler, we also need to specify some specific parameters. And here's a small example on how this code could look like. So we would now just have weights, which we are setting to 1s here, just a simple, stupid example, not very fancy. And then we would simply run this with a given number of epochs. We find the gradient, we find the change with a given scheduler, And in this case, we're using the Adam scheduler. We have the weights, which are now the weights minus the change. And then we simply print out the values after this training. And you see now the initial ones were set to ones, which is given by this matrix here. And this is the change which we get after we have called the Adam scheduler. And we just did 10 epochs in this specific case. And the cost functions, there's a series of cost functions. You will recognize the mean square error here. This is the ordinary least squares one. There is a log reg function here, and there's a cross entropy which we have. So these are all functions which you can use if you want to write your own code, or feel free to use this. And then if you scroll down here, you will then find the usage of automatic differentiation. So we would import from AutoGrad, we import the gradient, and we set up the cost function, which we now just call the cross entropy. And then we take the derivative, which is now given by the gradient of this cost function, which we have put in. And we have a set of target values, which you can see here. And then we have a set of A values, which are then spit in here. So we find the value at this set of variables A, and then we take the cost function derivative at this set of values A, and we just print out these derivatives. So these are just examples on how you can define a series of cost functions and use automatic differentiation to find their derivatives. Similarly, if you look at the activation functions, you can now set up different activation functions and set up their derivatives as well. So we have the different classes here. We have the sigmoid, the softmax, the relo, the linear relo. We have their derivatives, and you can keep adding functions here. For instance, you could have the ELO function with the exponential form, etc., etc. So the L relo is actually the leaky relo, etc., etc. You can add the tan-h. If you search for activation functions used in deep learning, you will find a plethora of such functions. Then, when we scroll down here, first of all, you will find some applications of these cost functions and also their derivative, as you can see here. So you have the derivative of the activation function, and here are just some simple test cases with a given input, and then the output which they give. So these are elements which you would need. And then we have the neural network itself. So this is a feed-forward neural network, and it has, as we have defined before, all the things you should know now: the dimensionalities, the hidden functions, the output functions, the cost function, the seed, the weights, the schedulers for the weights, the schedulers for the biases, and the different types of problems, whether we have a classification or regression type of problem, and all the other parameters, the number of epochs, number of batches. These are obviously overridden, these numbers here, the number of lambda parameters, etc., etc. So these are just the definitions, and you can see now the comments which you find here on how these different quantities are set up. And we can define the types of ways we estimate the quality of the model, whether we want to use the mean squared error or the accuracy or other types of values, functionalities. And here it runs over the number of epochs, the number of batches, and finds the, if you go down here, you will find the prediction part, you will find the feed forward part, as we have discussed before. And after the feed forward part, you will find the back propagation part. And all these kind of functions are functions which you can use. Here we have the accuracy for the case of a classification problem. We have a classification set, etc., etc. And when you run these codes here, you would. This is a simple case where we have set up a simple function, which is now given by a modified Franke function. It's called Skranke function here, just for the fun of it. And this is a two-dimensional function, and you're setting up the inputs, which defined by x and y. So keep in mind now that when you train a neural network, you're not going to feed a design matrix which looks like a polynomial tree, but you're just going to fit x and y, and you leave it to the neural network to figure out what is the functionality you want to reproduce. So it's a neural network which should figure out whether this is a 10th order polynomial, if that's the case, or a 5th order polynomial, etc., etc. So I just invite you to take a look at these examples. You can see now setting up simple test cases for this linear regression case. And you will find the scores with a given set of training parameters, lambda values, the number of epochs, which you can classify here. And there's another example where you take the Wisconsin breast cancer data. So this is highly relevant for project number 2. And you will recognize logistic regression here for the feed-forward neural network. If you just have, in this case, if you only have one output node, which is the case for logistic regression with a binary classification problem. And then you will find more examples here with the number of hidden nodes, the number of hidden nodes in the second layer, the number of output nodes. So this is the typical classification problem for a binary case. You have a multi-class classification here. And in this specific case, we are dealing with the MNIST data with 64 pixels, 8 times 8. This is a number of hidden layers, 2 hidden layers with 130 nodes, the number of output nodes. And then it finds the user, it uses a specific scheduler, it takes a specific value of eta, it has a specific value of the lambda parameter. But we would typically then run this for many more different variables. And you will also find the test of the XOR gate, which is often much more tricky. So we invite you to take a look at these programs. Feel free to use them as you want when you're developing your own for project number 2. So after this demonstration or overview of the codes which you can find in the lecture notes, we are going to look at how we can use deep learning methods like neural networks to solve differential equations. And we are going to start with looking at ordinary differential equations. And the universal approximation theorem states that a neural network can approximate any function at a single layer along with one input and output layer to a given precision. There are actually some interesting books. There is a book by Yadav and Kumar on Introduction to Neural Networks. And essentially, the slides which you find here give you an introduction to how to use neural networks. And the codes which you have developed for project number 2 can be used in project number 3. So project number 3 has a path which we call the ordinary differential equation path and partial differential equation path. This is normally a path which is very popular for those of you who are diving into studies of differential equations with, let's say, finite element methods or finite difference methods. And neural networks have become extremely popular in studies of differential equations, like the master thesis here by Marius was an application of deep learning methods to the study of turbulence in fluid mechanics problems. This is actually a very hot topic, especially in studies of turbulence in weather forecasting. And it forms also the basis for solutions of differential equations and what is normally called physics-informed neural networks, or just PINs, which stands for physics-informed neural networks. And that is a very, very popular research field where you can apply neural networks to solve classical differential equations like the Navier-Stokes equation for fluid mechanics, or if you're more interested in quantum mechanics, the solution of Schrödinger's equation. And these are all hot topics for research top studies and also for master thesis topics. So let's take a break here, and then we are going to look at how we can first solve ordinary differential equations with neural networks.